Okay, so let me try to fix what I goofed up. It's not a bad goof up, but then and then go on. But before I do y'all have any specific questions related to any of the?
No.
So it's not a bad goof up. You'll see why I goofed it up. What's funny is I've done this before and I don't think too much about it. And so the problem is nowadays, when you're a young professor, you get all cranked up when you make a mistake. When you've done it so many times, you're just tired. You're just like, go on. So sometimes some people get very anxious when they make a mistake, and I've passed that point. So, and maybe that's a bad thing. Okay, so I go from right here to maybe right there. I'm just trying to find, even a little further. Wow, okay. So maybe about right there. Let's see if that's, yeah, that's pretty much. So, and maybe this would help because, the thing is coordinate systems are very funny things, and like when you were talking about that v squared over r in physics, you always knew that was going towards the center of rotation, but you probably didn't put a basis vector on it, and that was probably, but now we're in this kind of concept where vectors, and then, do y'all have to take circuits too?
Yes.
Okay, so are you in that yet, or? Okay, so when you get in there, maybe near the end of this class, if you'll remind me, it's related to this material. I'll show you a quick way around a lot of that stuff, and some things they don't tell you that make it a kind of quick work to understand some of it. But if you can remind me, it's related to polar coordinates. So let's say you had a vector. Here's your use of r, and here's your use of theta. So we went through this thing where we had r was equal to this use of r. So before, you really didn't think too much about this or the directions if the thing is spinning around. But now you're like, okay, I need to have a direction. So in other words, if somebody said, you go 30 degrees from the x-axis and that's where you walk to go that direction, another person could just say this, you go UR. So then the next thing we did was this, and it ended up being this thing, and plus r times dur dt. And this is where I was focusing. So I made a little blunder, and I'll show it to you in a minute. So the question is, does UR change? And yeah, it does as it rotates around. So if you look at it from this perspective and you say, ooh, that's looking pretty ugly. That's not a straight line. Here's a straight line. Let's say you have the I vector and the J vector. So you're zooming up really close to here. You take this UR, it's just a point in a direction. So it could be anywhere. So I'm going to put it back here. And so, okay. I'm going to try to be better about this. So that's 1 unit, that's 1 unit, this is 1 unit. So each one of these, the unit, the length of I is the same as the length of J, which is the same as length of UR, which actually is the same as U theta too, but we're not talking about it yet. So they're all unit length. And then what we did, that's a straight line. Sorry about that. Came in here and we said this is cosine of theta, where that's theta. And then we came in here and we said this was sine of theta. That's a theta, not a key. So you say, okay, well, wait a minute. This looks like cosine theta I plus the sine of theta j. And so then you're like, okay, I broke that unit vector down. I slid it to here. It doesn't necessarily have to be 30 degrees. It could be anything. As a matter of fact, this was the key. that I ignored completely and I should not ignore. Theta can be a function of time. If it's not a function of time, it just sits there. And if it just sits there, then, in other words, if this doesn't change with respect to time, there's really not much use to use polar coordinates, because then you could just break it down into the I and the J and go on. The key is you may have a piece of rotating equipment or something like that, and it's spinning, and this point moves around this circular path, and that's a point where you might be interested in the information associated, or maybe it's your car going in circles. You know. So then the question is, now that we have this, and now that we have this, what did I goof up with? Well, I did this, u sub r dt. If I take a derivative, time derivative of that, it's true I get minus, derivative of cosine is minus the sine, but then I have to take the derivative of the theta itself, where, theta dot, or anything dot, is nothing more than that. And so I forgot that term. And then you take the derivative of sine, you get cosine theta, and then I'll put a box around it. I'm just putting a box around here to isolate these things, and then theta dot j. And so then we came back and we stared at u. We did this little drawing again with just u theta up there. And I'll get to working a problem in a minute. And in that particular case, I guess I could just use, I'll draw this one, and then I'll draw this one. So this is u theta. This is 90 degrees from each other. Here's ur, here's I, here's j. Now that's theta. So if you stare at u theta, you realize you get this component is cosine theta, and this component back over here is sine of theta, because that's of unit length. But this one's going backwards. Plus cosine of theta j. It's just simply breaking a vector using the sine and cosine. Then you stare at what you got here, and you stare at that, and you're looking back and forth at it, and you realize, oh, okay, ur dt, which is the same thing as ur dot, which I think that's what he writes in the book, is nothing more than theta dot u theta. I forgot the theta dot. I should not have, but I did. So if you need to kick me after class, that's okay. I'm pretty numb now. So
can you give like an example of theta dot?
Exactly. We're going to do that. Let me finish the other part, and I'm going to work a problem with this, and we'll cover the whole thing. So it makes more concrete sense, because I think I'll have plenty of time to work. As a matter of fact, I think I know one of the ones that's in the homework. I may not have the right numbers, because he may change the numbers, but I can just work that one.
Okay.
So what happens in a minute is, okay, so things I want to save in my brain is this. ur dot is equal to theta dot u theta. The other thing I'm going to save, and I'm writing this up here because I'm going to erase everything and then I'm going to make that problem. And then u theta dot is equal to minus theta dot ur, and I'll show you this one in a second. So these are our two things that we're going to use. Okay, so now we look at this one, and you're like, hey, I know I'm going to eventually have to take this derivative. So what is it? Well, derivative of sine is cosine theta dot, and put a box around it again, I plus derivative of cosine is minus the sine, and theta dot j. And if you stare at this real quick, you'll notice this, there's a minus in front of both. There's not a minus here. So in fact, u theta dot is nothing more than minus ur with a theta dot in front of it, and which is what I wrote up there. So it's basically that. And I am remiss in not writing this, and not writing that, nor writing that one, and nor writing that one. So if you're okay with that, now let me go through a very quick derivation of the two things that we'll need, and then we'll write our problem, and then we'll solve our problem. We should be able to get done with it in time. So I got enough space down here. I think I can do it right here. So, okay, so I'll just go ahead and, So I'll have this. This is my R. It's a scalar value, which actually, and I'm going to go ahead and put this in here. It's time dependent. It could grow and be further or shorter. In other words, let's say you had a spiral and it's going that way. Then R is shortening with respect to time. Then UR can also vary with time. So both of these are dependent upon time. And so it can spiral out, spiral in, do all this sort of stuff. But you might be interested in the velocity. So the velocity is nothing more than R dot, which is nothing, the vector dot, which is nothing more than R dot, UR plus R, UR dot. That we say, oh crap, we did that already. I look up here and I grab it. And this is what I get. R dot UR plus R theta dot U theta. Where did I get that? I got the UR from right here. Just copy those two right down. This is what you'll see in the book. That equation is right in there. Units. Let's look at units for a second. I'll just say, this is feet per second. This is feet. And this is radians per second. Since radians don't have any unit, this becomes feet per second. I'm going to use that in a second to make sure the accelerations, I'm going to check myself on the acceleration. So the units have to work themselves out. The theta is usually thought of as in radians, but you can use degrees. But when you put it in like this and stuff, you got to make sure you're using the right thing. Better. I know it's hard to do this, but it's kind of better to use radians all the time. But the book doesn't let you do that either. So now you're looking for acceleration, and here's where things get dicey. So what you want to do is take the time derivative of the velocity. So now you got this one and this one and this one and this one and this one. Okay, so now I'm going to have a lot of things to write, so I'm going to erase all that, quickly go through this, box the acceleration equation, then start the problem. So if you don't mind, I can sort of give up on all this junk. Because this is the space I'll probably need to put the problem in. So if you do this, what is it? Well, you go through R double dot, UR, take the derivative of that times that plus that times the derivative of that, R dot, UR dot. I'm done with that term. Now I'm going to start here, plus R dot, theta dot, U theta, derivative of that times these two, derivative of that times these two, derivative of that one times these two. Now I've got R, that doesn't look like an R. Now it maybe looks like an R, double dot, then times the U theta plus R theta dot U theta dot. Here is where I've got to focus on, to use those two equations to get rid of the time derivative of the base vectors. So if I'm going to do all this and just copy that down to here, hopefully not making a mistake, plus r dot ur is theta dot u theta. Okay, so I just copied this from there down to here. I'm done. Don't have to do anything here. Don't have to do anything here. Okay. And we'll make sense of each of these terms in a second. Okay, now I got to go get here. I got to go up to here, get that, put it down here. There's a minus in front of it. So I got to get rid of this. And then I got to put a theta dot down here. But wait a minute, I already got a theta dot. So now I just square it. And then I replace it with UR. So you got this big long equation in which, if you stare at it for just a moment, you'll see a couple things. You'll see that. And then you'll want to gather the terms so that you have, you know what? I'm going to move this equation up, and then I'm going to put the acceleration equation right here. So I'm going to go ahead and do this. Then I can have all the equations right under each other, and then I can erase all this other stuff. Plus r theta dot u theta. And then I'll box this one. And I'll say, okay, so here's where I'm going to put the acceleration. So I'm going to copy these term by term, put them right there. So what I'm going to do is I'm going to focus on u sub r and then u theta. So if I do that, u sub r sits right here and it sits right there. Those are the only two places it sits. So I have r double dot and I have minus r theta dot squared. This term might look new to you, but you've seen it before. And you may not recognize that you've seen it yet. So let me finish this, I'll show you what that is. So then, now I've got to do the u thetas. Usually, in the book, he writes this one first. R theta double dot plus, and you got two of these now. 2 r dot theta dot. Now let's look at our units. And all of our units, if we are in here, we got to be feet per second squared. That's obviously, there's feet, that's radians per second squared, which will square your second underneath, so we're good there. This is feet, this is radians per second squared. This is 2, which doesn't have any units. This is feet per second and radians per second. So everything comes out as in the right units. So we're feeling pretty comfortable. But we got this big, long, awful, nauseating equation, but it's actually not that difficult. So let me address something. Let's say you have a wheel. This is not the problem I was going to solve, but let's just say you have a wheel that is spinning around. You paint a little spot on the end of it. Or maybe, okay, so maybe it's you standing there slinging something around. So you're putting a force, a centrifugal force is pulling this way. You knew this. If this is R, that's the centrifugal, I'll just say centrifugal acceleration. You figured that out from Physics 1. So shouldn't that produce the same thing? And in fact, it does. So as you sling this around in a circle, let's say the circle is constant, so the r dot is nothing. So the r is maybe 2, just making that up. So the r is 2. Let's say your velocity, your magnitude of your velocity is 5, just make that up. So now you look at this first equation. Okay, so if I go to this, I can sit there and say velocity is equal to r dot ur plus r theta dot u theta. Now, let me I kind of cramped this right here, so let me move it over. So we're still focusing on this. We got to be able to say whatever you learned before, you can't really learn that it's something new. It has to be the same as it is there as it is here. And so now you're saying, oh, I got this coordinate that does like this and does like that. So let's stare at it here. First, you said the ropes that you're slinging around is not growing or shrinking. So that term is 0. So you're just slinging something around, holding the rope. Maybe there's a big brick on the end of it, and you're going to sling it until it speeds up. But say you're just spinning it at constant speed. So then it says the velocity is equal to r theta dot u theta. But wait a minute, this points in the direction. So this is pointing in that way. Well, that's the tangent to this path of this rock that or brick you're flinging around. So now I have the fact that the magnitude of the velocity, okay, so if I did this and said, what's the magnitude of this? Well, that vector has a magnitude of 1, and so if it does, these are two scalars, they always have the same thing. So it ends up being the velocity is equal to that. The r, the distance out, times the spin rate. So we said this was 2, and we didn't say how fast we were spinning. So let's maybe say, I've already used 2 and a 5, so let's maybe it's, well, you know what? I'm going to say it's 20, because then it makes, so you're spinning it and its velocity is 20. So this way I can get 20 out of it. Otherwise, I got to figure out something to multiply times 2 in order to get 5. And I don't want to do that. So this means this is 10 radians per second and 10 feet. Now, if you want to put a strobe on it, you can do this. 10 radians per second. There are 2 pi radians in 1 revolution. What should I say? Revolution. Then this is how many revolutions per second. But most of the time you want it in RPM. So you want to get rid of the second. 60 seconds over 1. Okay, wait a minute. That was supposed to just be minute. So you can do 10 times 60 divided by 2 pi, and that's, okay, so that'd be 600 over 2 pi RPM. So if you're spinning this thing and you're able to get that's what the revolutions per minute is, backs down to 10 radians per second. So you get 20. Before you were told 20 squared over r, which was 2. Okay, I've kind of made it. Okay, so I got 20 times 20 over 2. That cancels down to give me 10, so I got 200. Is that right? Did I do that right? So, I hope I did. So, the acceleration term should give you that 200. So now let's look at this. We derive this. That's enough time on the video to look at it. So let's look at that in each one of these terms. If r dot is 0, and in other words, the rope isn't getting longer or shorter through time, then you can pretty much say our double dot's gone. So if you look at the acceleration, you get this. With just these two in there, you get minus r theta dot squared ur, and then you get plus r theta double dot u theta. Why? Because that term disappeared and this term disappeared. Now let's look at this one. If you're spinning at 20 or 10 radians per second and it's constant, then that term goes away. And so you're left with just this one term. The brick is on the end of the rope is not going longer or shorter, you're spinning it at a constant rate, that's the acceleration. Now let's look at what that becomes. It becomes minus r, which in your case was 2, and theta dot squared, which was 100 squared. No, I'm sorry, it's 10 squared, which is 100. So it becomes nothing more than minus 200 use of R. Why does this one have a minus and that one doesn't? Because you were kind of told in physics that the centrifugal acceleration is going back towards the center of the thing. Now you're told you have a coordinate system which points out, but the minus makes that 200 flip over and point in the same direction that you were taught in physics. So it's exactly the same thing. There's nothing different, there's nothing new. It's just some new terminology. So when you see this is the one term that you learned before. V squared over rho, or R. That's all it is. Now you've got the ability, with this equation, you've got the ability to deal with multiple variables. One that they could be spinning up, slowing down. The rho could be extending. In other words, you could spin it and then extend it. Or like a skater. You know, a skater will skate in a circle and then they draw their arms in, and that suddenly they start spinning up. You know, it's just the dynamics of the situation. So now let's look at a problem. Did what I say make sense? I mean, so it's really nothing new. Well, okay, let me rephrase it. We're extrapolating from what you already knew. It's just now we're doing it in a coordinate system, and now we can do more complicated problems with it. So there are terms in here that you've seen before. So it's just unfortunately, you know, you got to start somewhere, and sometimes it's hard to swallow something like that right off in physics. It's better to do the V squared over R and then grow from there, maybe. So the problem that's in the textbook, okay, I'm not a great drawer, so what it is it's funny. Okay, so let me write the equation and then so R is equal to, and you got to make up something, 0.5, 1 minus cosine, I think it's 2 theta. Or is it theta? It may be theta. But you know what? I'm going to leave it as 2 theta. So you have R listed this way. So if I put out here, let's try to get some points here so we can map this path out on this. Okay, here's X, here's Y. So let me just list a few. If I put in theta equals 0, I think cosine of 0 is 1, and so I get 1 minus 1, I get nothing. Maybe I better make it so that it has a value of R out there. So I may be adjusting things a little bit. So what I might do is put the 0.5 on the inside. So in other words, 1 minus 0.5 cosine theta. So if I put in 0 now, I get a half. So I don't know where a half is. How about that? So now if I go to 45 degrees, well, you know what? To start off, let's just do this. We'll just do this, and we can do more complicated as time goes on. If I go to 45, I get 1 minus, okay, so theta is equal to 45 degrees. I get R is equal to 1 minus 0.5 over square root of 2. Okay, let me just stick that in this funny thing. I know that I can use the calculator, but I don't want to. Okay, so that becomes 0.646. That's close enough. So let's say theta is equal to 90, gives me R is equal to 1 minus cosine of 90. So if we remember this, cosine starts here, it goes to here. That's your 90, that's your 180, there's your 270, there's your 360. I'm not going to, well, I don't know. So anyway, it goes to 0.6. Okay. So, all right. I didn't finish that, did I? R is equal to, put in 0 for theta. You get 1, get 1 minus this, you get 0.5. So it's 0.5, it grows a little bit to 0.6. So if this is 0.5 and I'm like here, it's like right here. So it's a little path like this. I don't know where it is at 90 yet. Cosine 90 gives me nothing. I get to 1 minus 0, I get 1. Okay, so if this is 0.5, ouch, I kind of, okay, so then it kind of grew to about right here. So you can see this R is following this path. Okay, so, I don't know, what's 90 in that? 135. So here we go. 1 minus 0.5 cosine of 135 degrees equals to, I'm going to make this thing calculate that, if it'll do it. Will it do it? It will. 1.35355. So it's growing even more when we get out to here. So you can kind of see the path of so this, let's say this is a marble and it's following along this path. So what it is in the book, what he'll show is this. He'll show a rod that rotates, has a pivot right here, has an arm that goes out here, and then what it has is this little sleeve on here so that this thing follows this path. Is like a little hook in there, and it basically follows that path. And the other thing, it's a hook on this rod, but this thing can slide off that rod and slide on it. And so then he'll say something like, okay, theta dot is equal to 2 radians per second. And then he'll say theta double dot, we're just going to make it 1 radians per second squared. I don't know the numbers. I don't know. I think he has a 0.2 or something like here instead of 0.5. And there may be another number right here too. But the key is there's a cosine, there's some, I think there's a name for this path, a limricon or something. I don't know. And then he says R is this, and he says find, so the question will be find the velocity vector and the acceleration vector when, I don't know, when theta is equal to 45. So if you look at this equation, you'll see something interesting. Look at each of the terms in here, and I'll classify them. Inside the velocity equation, the only thing you need to know is R dot, R, actually I should list those in reverse order. You have to know R, you have to know R dot, and you have to know theta dot. If I had those three numbers at 45 degrees, I just insert them in this equation and calculate them, and I'm done. Okay, if I'm in acceleration, you'll see R, R dot, and R. You'll see the R dot, and the theta dot. But now you see another two terms, this one and that one. So in addition to that, you will need to know this and this. So I'm just quantifying exactly what you need to know in order to solve that. And that's it. So the question is, how do you do this? Actually, it's not that bad. I'll tell you how easy it is. Here's 2 radians per second. Why? Because he gave that. Here's 1 radians per second, and that's it. Now you got to deal with R. Okay. So there are 2 ways you can do this. One is you can put a box and work it out, or I'm doing it like this, where these are evaluated at 45. So here's what I have to do. I have to say R is equal to, and I'm just copying it down, 1 minus 0.5 cosine of theta. Well, I already put this in, 1 minus 0.5 cosine of 45 degrees, and I got oh, wait a minute, 1 minus 0.5. Is that what that number is? Did I do that? I think I did that one. Okay, so that is 0.646. Now I got to do this one and that one. These are the 3 easiest ones. Usually those are the easiest ones. The next one, like, okay, I got to do this. I got to do just a simple derivative. I got to do a derivative of the r with respect to time. And this is the equation I got to do that on. But I know, that theta is a function of time. So what I have to do is take the time derivative of 1. That's pretty simple. But then I have minus 0.5 times the derivative, theta dt times the derivative of the thing in there, which is one of the things I forgot last time. Sorry about that. So this is that chain thing. So you have this. You don't have the derivative with respect to theta, but you can do this, and the derivative of that ends up being a minus, which clobbers that minus, and so you get a 0.5 sine of theta times theta dot. Now that's a standard definition in that this, you vary theta and you get a different r dot. But specifically, the question was asked at 45 degrees. So what do? You just say r dot is equal to 0.5 times sine of 45 degrees times theta dot, which was given to you as 2. Now I'm going to make it calculate that. I like this thing because it makes things go faster in here. Uh-oh, it may not have picked that up. Oh, it did. So it says that's 0.707, 2 over square root of 2, which is kind of weird. 107, why does he not extend that? Okay, 0.707, 107. Okay, so the last thing we got to fill out is this. And what I'll do is, since the edge of the board's over here, I'll kind of jump in here and fit it in right here. We've copied these over into here, so I don't need these anymore. And I'm going to use this equation. So let's see. R double dot, and here's where the problem comes in. With respect to time of 0.5 theta dot sine of theta. Now, I'm copying that right in here. And I'm moving the theta dot in front of the sine. Man, I'm getting hot in here. And so, which is okay, I guess. So, heat, air, they've got all sorts of problems. So how do you do that? Well, it's easy to do that one, that's nothing. So here you take the derivative of it. So you do 0.5 theta double dot sine of theta plus 0.5 times theta dot times the derivative of sine with respect to time, but you don't have that. But you do have this. And so you can get 0.5 theta double dot sine of theta plus 0.5 theta dot squared, because you got one here, you got one there. Derivative of sine, I think, is still cosine. You can tell me if I'm wrong. So from a mathematical viewpoint, this becomes 0.5, and now I'm just going to borrow the numbers. That was 1. This is sine of 45 degrees plus 0.5. Theta dot was 2 squared cosine of 45 degrees. Let's see what it does with that, because now I've got parentheses there and not a parentheses there. Let's see what it does. Oh, I put a parentheses there anyway. So it came up with this R double dot of 1.76777. 777. Okay, so now that you've done that, now it's just insert those 5 numbers into those 2 equations. And so my graphic is not great, so I'm just going to use this space to do that. Velocity vector is equal to R dot point 707 107 times UR plus R, which was 0.646, times theta dot, which was 2, times U theta. And that's your answer, barring the fact that you need to multiply 2 times that number. Now the next one was acceleration. What's the acceleration right there? Well, it's R double dot 1.76777 minus R times theta dot squared. R, which was 0.646, theta dot squared, which was 2 squared, and UR plus R 0.646 theta double dot, which was a 1, plus 2 times R dot, which is 0.707, 107, and then theta dot, which was 2. And all that here, there's so much junk here, just going to do that. And there's your acceleration, barring the fact that you multiply all that out, because he's going to want you to put in 2 numbers. He's going to want you to put in probably this number, probably that number, and then that number. You know, he may actually make 4 places there. So what you've got here, this is the v squared over r. The reason you have acceleration in the UR direction that is in addition to the centrifugal acceleration is the fact that the slider slides out. In other words, it's this close at 0 degrees, it's this, then it's that, then it's that. So the R is growing. As you're spinning, it's growing out there. So it's kind of like, you know, you're growing as you're spinning. So this is the growing as you're spinning. That's kind of a weird terminology, but that's the reason you have that. So you're accelerating out that direction. But this acceleration is the centrifugal. Then you have this part, which is the thing that it's spinning and it's speeding up as it's spinning, but you have these 2 parts, and this is kind of hard to describe. It's kind of a cross acceleration term, but one way of thinking of it is, it's really hard to classify this one as much, but if the R wasn't increasing, this would be nothing. And then you would only have the acceleration tangential to that path. So does this kind of make sense? I mean, it's just a bunch of math, but if you classify what you need to do, 1, you got these 2 equations. 2, somebody's going to give you, and I've erased it already. Oh, well, here it is. Somebody's going to give you some equation for R, and usually they're going to give you this and this. And then you're going to have to differentiate this thing twice. First, for the R dot, and again for the R double dot. Once you do those two, it's just a plug and chug.
And how does it apply to circuits? You said
Okay, so how it applies to circuits is, let me kind of get, if you don't mind, I'll take this spot. I don't have a lot of time, but I can show you. You know, in circuits, okay, we're used to seeing this. I'm sorry, that's supposed to be X and Y. In circuits, they do something that's real and imaginary. So they do real, imaginary, and then so what you're looking at is things that are going in a circle. The voltage might go in a circle.
I'm not sure I understand.
like an AC current?
Yeah, like an AC current. And so what happens is they break it into this some number times e to the j omega t. Now that's not the same j as our coordinate direction. That's an imaginary number. But it turns out that if you go look at this, that and these two, if you really wanted to spill the time, you'll see that those equations turn out to be the same. There's a kind of a loophole here, but that's not associated with either one of these. But they're using this polar coordinates, and they're using. If you look at it, you're like, oh, well, wait a minute. That's like the polar coordinates. So you can see how there's a relationship between this and sines and cosines. And you're looking at it as something like sine omega t plus the j times cosine omega t or something like that. And you're like, what the crap is that? Well, it's basically the same thing. You've got a vector sitting out here, and there's a part that's projected back here, and there's a part projected back here. And if you stare at it long enough, you're like, hey, wait a minute, that's the same thing that this is. So these coordinates, the polar coordinates and the things you're using there, they're the same. It's just they don't call it X, and they don't call it Y, but they call it real, and then they call it imaginary. And so if you go, if I don't know when you're taking circuits 2. I don't even know when this might show up in circuit 1. I don't know. Oh, it doesn't? Okay. So when you look at it, just go sit at the cafeteria one day and look at this, and then look at what they're doing, and you'll see, like, hey, wait a minute, it's the same thing. It has a totally different connotation because they're not looking for velocity and acceleration, but the coordinate system that they're both using is the same. Where we go with it is one direction, where they go is another direction. And it's basically, you'll start seeing the e to the j omega t. And you'll start seeing, hey, wait a minute, there's a sine and there's a cosine. Well, actually, there's a cosine and there's a sine. And you'll say e to the j omega t is basically these two components written in one. And you're like, oh, okay. So then they're going to say, well, let's add two vectors. And so what they'll do is they'll say, I have a current coming in like this, and I have another current coming in like that. So then they'll say, well, let's add this to this, and let's add this one to that one. And it turns out, if you look at it, if the omegas are different, this is a compact way of writing that coordinate I had, which it's gone now, but remember the use of R was cosine plus sine to the j. This can be compactly written back into that form. And so you'll have to stare at it and think about it, but once you get that familiarity with what's going on, you're like, oh, okay, I kind of see a similar. You can't really go get this and use it, but what you can do is see, there's a certain part where you start looking at stuff and you might feel more comfortable if you've seen it before. Like the v squared over r. Like if I just wrote that stuff down and didn't say anything, you'd say, what the crap's going on? Well, there is part of this you've already seen. And so, I'm hoping, I don't know.
And you're saying that the bottom part, V squared over R, is that entire thing? 1.7677?
Oh, well, the V squared over R becomes this one. So that's this one. The 1.76 is the fact that as he spun, the thing moved away from the center. So the first one we were spinning it, and the rope was staying fixed. Now it's spinning along this axis, and when we move up, it's moving out the axis.
So it's expanding?
Yeah, it's moving out. So that's what that term is that it moved out. The R double dot is because the R got bigger as we move like that. And so, so I know it's a lot to swallow, but when you boil down and look at the problems, what you got to do is come up with 5 specific numbers. And then you got to put them in these 2 equations, and then you fill them out. And so, technically, unfortunately, you could probably do all that without understanding a single solitary thing about this. I mean, and that's the unfortunate thing, but once you get that, that's all you have to do. For the homework, that is.
Okay.
So I guess I'm done. I went too long. Yeah, and you probably got to get to another class.